Sentite? Sì. So in this case, the symmetry is not realized in the spectrum. The consequence of the symmetry is the presence of massless particles, which are called Nambu-Goston boson. And this is also a symmetry of QCD. If you take zero quark mass, then with two flavors you have this symmetry, which is broken to SU2 vectorial. And so you have three broken generators. And the Nambu-Goston boson are the three pions in QCD with two flavors. This is one consequence of the symmetry. There is another consequence, which is the existence of low energy theorem. If you take soft pions, the scattering amplitude is zero at low energy, and you get Adler zeros. If one introduces small mass to the pion, which breaks explicitly the chiral symmetry, that gives then one gets, instead of getting zero, you get the two Weinberg scattering length, which go to zero when the pion mass goes to zero. Then there are space-time global symmetry, and the most notable is the conformal symmetry. It is a classical symmetry if the action doesn't contain a dimensional quantity. In general, it's broken by anomaly in the quantum theory, because in general you need to introduce mu, a dimensional quantity, mu, when you do the renormalization. And it can also be explicitly broken by mass term. But if you don't have explicit breaking, if you give a vacuum expectation value to some field, scalar field for instance, then you get also here a unique Goston boson, which is called the dilaton, which has also a universal low energy behavior. And although you break 5 generators, you get in this case, since it's the space-time symmetry, only one Nambu-Goston boson. And one can derive the universal soft dilaton behavior from the conformal word identities. In general, this symmetry is broken, and the dilaton gets a mass which is proportional to the beta function of the theory. There is a theory, however, n equal 4 super-Young Mills, where the dilaton stays massless. And in this case, you have, in the case of n equal 4, you have 6 scalar field, and one of these scalar field gets a vacuum expectation value. You go to the Coulomb branch, and in this case, both the conformal symmetry and the R symmetry are spontaneously broken. And the one which the dilaton is the object which has the vacuum expectation value, and the other 5 field belongs to the coset, and these are the Goston boson of broken R symmetry. So in this case, you have you break together the conformal group together with a global symmetry, SO6. And because of this double breaking, then as a consequence, I mean, this has been shown in this paper, the 5 Nambu-Goston boson in this case do not have Adler zeros. Then you have a local internal and space-time symmetry. So a local internal symmetry requires the introduction of the massless gauge field with spin 1. And if you have a space-time, you need to introduce a spin 2. And in both cases, local gauge invariant is essential to essentially reconcile the theory of relativity with quantum mechanics. In fact, you have a complete relativistic description with A mu and G mu nu. So that you can describe the physics in terms of this, but the degrees of freedom are only, in 4 dimensions, only 2. And gauge invariance is what is needed to have both a description which is a relativistic invariant, and you have only a physical positive norm degrees of freedom. Another consequence of gauge invariance for photon is charge conservation, while for graviton is momentum conservation. And finally, there is another physical consequence, which is also in this case the existence of low energy theorem for photon and gravitons. And this goes back to Francis Law in 58 and Weinberg in 64. Now, the interest of soft theorem was revived a few years ago by the paper by Cacciazzo and Strominger, and that opened the way to many papers that I'm not citing here. Now, they studied the behavior of n graviton amplitude when momentum of one graviton goes to 0. The leading term, which goes 1 over q to minus 1, was shown to be universal by Weinberg in the 60s. And they suggest a universal formula for subleading, and they also speculate that as the leading term, it may be consequence of BMS symmetry of asymptotically flat space-time. And this has been claimed later in 4 space-time dimensions to be a consequence of BMS. Now also the sub-subleading has been shown to come from BMS from Einstein gravity. Now, in this talk, I will use a completely different point of view. If you give the structure of the 3-point function, I will show you later on what that means. Then I will show that those conditions for the graviton, so you have a graviton and many other particles which can be anything. Well, in the talk, I will consider scalar particle and massless particle, like photon, graviton, and so gluon, graviton, and dilaton, and so on. And then, using this equation, one can completely determine giving this equation and the structure of the 3-point function, one can completely determine the order q minus 1, q to the 0, and q1 of the symmetric part of mu nu in terms of the amplitude without the soft particle. Q is the momentum of the soft particle, and mu and nu are indices of soft particle. Now, this can be rephrased in 2 ways. Either you say that in the way that I formulate, or you can say that you can determine from gauge invariance only the first 2. The third one depends, of course, on the theory that you are considering, but once you give the 3-point function, also the third term is determined. They also determine the term of order Q0 of the antisymmetric part of this in terms of the amplitude without the soft particle. So for B mu nu, which corresponds to the soft limit of Kalb-Ramond field, the term is 0, and that of order Q is not fixed. Now, the soft behavior for graviton, dilaton, B mu nu obtained in this way are confirmed by explicit calculation in string amplitude, where the other particles are mass scalar, like the tachyon, or massless graviton, dilaton, and B mu nu. However, as you will see, this procedure can be extended to massive particle with any string, although it's more complicated in a straightforward way. Now, the soft behavior obtained in this way is valid not only for the tree diagram, but also for loop diagram, when the theory containing those soft particles is free from ultraviolet and an infrared divergence, like, for instance, n equal 4. The soft theorem is kept also at the loop level if there are no ultraviolet divergence and the infrared divergence do not depend on a number of external legs. I will explain that later on. And this is the case of the bosonic string if we compactify in 26 minus d, so we have 26 minus d compact directions, and we keep d bigger than 4. And again, the soft behavior is confirmed by explicit calculation, and also the string correction turn out to be determined by the structure of the three-point function. It turns out that the soft behavior of the gravity dilaton involves the generators of scale and special conformal transformation. And then we'll consider a conformal theory in d dimension where those generators are spontaneously broken. And in this case, you have a Nambu-Goston boson, which is also called a dilaton. Now, in principle, these two dilatons have nothing to do with each other. They have, however, a common property. They are coupled, both of them are coupled to the trace of energy momentum tensor, and that is the origin of the name, although nowadays the name may be confusing. And in fact, the string dilaton is coupled to the trace of the target space energy momentum tensor. Its vertex operator is essentially the trace of the energy momentum tensor. Then, because of when you break spontaneously the conformal group, you can use Worth-Takahashi identity, and you can show that the low energy behavior of the field theory dilaton is very similar to that of the gravity dilaton, but not exactly the same. And I will discuss difference and similarities. Okay, that's the introduction. So let's consider the simplest case, which was discussed by Francis Law in the 50s. So you have a number of scalar particles and a photon, and so you have a contribution given by when the photon is attached to one of the external legs, and the contribution where the photon is attached to the gut. That's what people call this. And then the scattering amplitude can be written as the sum of poles here. This is the electric charge of the particle. And this is the amplitude with K1, Kn, and then the particle, which is the pole, has momentum Ki plus Q, and then the term without poles. Then gauge invariance implies that you saturate with Q mu, you get 0. And so you can expand around Q equals 0. You get this term, and this term, and this term, and then order of Q squared. Now, at leading order, if this is 0, you have to require that sum of the charge is 0. And that is charge conservation. At the order Q, you get this equality. And this equation tells that this n is entirely determined in terms of Mn, so the amplitude without the soft particle, up to potential p's that are separately gauge invariant. But you can see that the only potential p's are of this kind, where A mu nu is an antisymmetric metric. So this is order Q, and so will not contribute to the order when I take Q equals 0 here. And then you can take away the Q mu, and you get a relation between this term at 0 momentum in terms of the derivative of the amplitude without the soft particle. Now, if you insert this on the original expression, that you get, this is the pole term, and the pole term generates a term like this, and the other one gives this. So in the end, you have a contribution of the orbital angular momentum. And essentially, gauge invariance tells you that the amplitude with a soft photon is entirely determined in terms of the amplitude without the soft photon up to the order Q to the 0. And that is the Law theorem. Law theorem is unchanged at the loop level, this is the abelian symmetry. And you can get an amplitude saturated with the polarization, and you get the two soft terms. This is order 1 over q, and this is order q to the 0. Actually, from gauge invariance, you can get more than that. And this is a paper from people from Taiwan, in which actually you can completely determine, if you write n mu nu, and you expand in terms of these indices, then gauge invariant fix completely the completely symmetric part of the n mu nu. And so you get this is equal to the completely symmetric part, which is given in terms of the amplitude without the soft photon. But then there is the antisymmetric part, which cannot be determined from gauge invariance. So it depends on the particular theory.
So for the photon subleading soft theorem, are you assuming minimal coupling of the photon?
Sorry?
For the photon subleading soft theorem,
yeah.
to the 0, are you assuming minimal coupling?
No.
But if you have a coupling to a magnetic moment, wouldn't that contribute in order to the 0?
Then the first term is not present, you say.
No, minimal coupling plus a coupling to magnetic moment.
I'm assuming that there is a minimal coupling, and then there is a term. Otherwise, you cannot relate the two if you don't have a minimal coupling. So if you put, so you get this, and then if you go back to the amplitude, you get this. So this is a completely symmetric part, and this is the antisymmetric part. And then if you multiply the amplitude with something which is completely symmetric, you can check that all the derivative can be determined in terms of the amplitude without m. And this is in agreement with the result of this paper, which is obtained with different method. Then let me go to Graviton. In this case, also you have a pole term and a term which has not any pole. And then you impose gauge invariant, you saturate with Q mu and Q nu. You get this equation. Here, let me stop for a moment and specify what I'm doing. In general, gauge invariant fix, you have to add a term. In general, this times this is not 0. In general, you may add a term like that, where f is in general an arbitrary function. Now, a term like that is irrelevant for Graviton because you use this condition. But it would be relevant for dilaton. And so, in general, for dilaton, you cannot derive a soft theorem unless you say something about this function f. Now, it turns out that if you do explicit string calculation, for the moment at the tree level, this shows that this term, if you have only closed string, is not present. But, however, if you have among the other state also open string, then this term is present for open string. And we will see that this term is important as for the case of open string, an important physical interpretation. Also, explicit string calculation at multi-loop level in the bosonic string shows that there is a term like that appearing in the case of the dilaton, and also in this case, this term has a very simple interpretation. So these terms are needed, but that are needed and are present in certain particular case, but in general are absent. And this is, it's not clear why is that. Now let me go back to the gauge invariance equation, and if I expand this equation for the term with q equals 0, it's 0 if you need to have a momentum conservation. So the soft theorem implies, for gravity, implies momentum conservation. So that means different couplings to different particles that would have prevented this. And so that means that graviton must have a universal coupling. Then you have this equation at the first order, this equation at the second order, and also the equation for the other, for mu instead of nu. If you use all these equations, you determine the soft behavior to have this form. And so you get the 1 over q term, the q to the 0 term, and the q to the 1 term. And this is q to the 1 term. And this is the precise normalization. And of course, this satisfies this equation. This is the way it has been obtained. And this is actually the soft dilaton-graviton behavior of an amplitude with n tachyon in the bosonic string with no alpha prime correction. Now, the physical condition for the graviton give you the three terms. And if you saturate with the dilaton polarization, then you get a mass term here. The tachyon have a mass different from 0, so you have a term like that we will see appears also on the field theory dilaton, and then order q to the 0 and q to the 1. So let me go on and discuss the gluon. In the gluon, I considered three-level color order amplitude, where the gluon, so the gluon n, it's soft. It can be coupled only to the neighbor legs, so to the leg 1 and the leg n minus 1. And so you have only two poles in the color order amplitude. And then you introduce the spin, the spin angular momentum, the spin contribution to the angular momentum, and you have to introduce here the three graviton vertex that, in case of you have on-shell particle, and also when this particle is a bit off-shell, you can write in this form. So there is a term like the scalar plus q times the spin part. And that for the two neighbor leg, and then the part which has no pole. And then you impose gauge invariance. You see that the leading term for q equals 0 cancel between this and this. And the term of order q is this one. And so again, n is the term in terms of m without the soft particle. So this is the amplitude. And now the difference with respect to the scalar particle, that you have not only the orbital but also the spin angular momentum. And then you have to multiply by the polarization, and you have to go through with the polarization through this. And you can check that the polarization, so instead of writing in terms of sigma, you can write sigma in terms of this object here. So when you saturate the amplitude with the polarization, this is the spin contribution. And so you have the two, the 1 over q and q to the 0 term like that, and this is the total angular momentum. You can go on and do the same thing for graviton, where all the other particles are graviton, or even, well, in this case I consider graviton, but in the string you could have also dilaton. So all the other particles are massless in any case. And so this is the graviton 3-point function that on shell is the product of two gluon. And so you go through the procedure and you arrive to this expression. So again, n plus 1 for the soft graviton is in terms of, well, here I am not specified. I have imposed the condition and I am not specified yet. So this could be a graviton, but could be also a dilaton. Now, there are all these terms. Here, this operator in general acts also on this. If you don't let him to act, you can cancel all these terms. So it can be written in a more, this double dot means that the first operator acts only on this without acting on the other one. Now, for the graviton, you have to impose this condition. You have to pass again the polarization through this sigma matrix, and you get these three terms. And these three terms follow completely from gauge invariant and agree with those computed by Cacciazzo and Strominger for d equal 4. And remember that this is the sum of the two, orbital and spin. If you project along the dilaton now, this is what you get, and we checked that doing explicit calculation in string theory, you get the same. And in case of the dilaton, you never get alpha prime correction. That's another mystery. You'd never get. So if you look at the Kalb-Ramond field, then you get again the pole term, and now you have to treat this different from this, not to have a symmetric object. And the leading term is symmetric, so it doesn't contribute. So you get this three term. And this piece is not gauge invariant, but you can make gauge invariant adding this. And in general, you could add this, but then the gauge invariant condition fixed the n mu nu at 0 to be 0, and this has to be a completely antisymmetric tensor. So that's what you get. And this result is obtained from gauge invariant, has been confirmed by Iguchi and Kawai using OPE with a vertex operator. So the two procedures seems to be consistent. This term here is completely antisymmetric and cannot be fixed by gauge invariant. If you multiply it by Q mu, you get 0. So cannot be fixed. And in string theory, the sub-leading term cannot be written in a factorized form, and actually contains a term with the Bloch-Wigner dialogue that is gauge invariant by itself. And so there is a unified formula for graviton, dilaton, and b mu nu. Now let me go now to string theory. So the string theory, the soft theorem was already discussed in the 70s for the dilaton by Ademollo et al. And Joel Shapiro. But after the paper Cacciazzo and Strominger, people looked again in string theory to see how string theory realized the soft theorem. And there have been a lot of paper. And what one can do, you can compute an amplitude with a massless closed string, another particle, and then look explicitly what is the soft theorem. And the leading and the two sub-leading terms are exactly those derived imposing gauge invariant, apart from string correction in the sub-sub-leading term. So if the soft particle is a dilaton and the other particle are a tachyon, then at the tree level you get, that's the expression that you get, and the mass is just the mass of the tachyon, and Mn, the n tachyon amplitude correctly normalized is this one. And notice that there is an alpha prime here and there is a kappa d here. So this alpha prime is relevant to do the field theory limit. When when the other particles are massless, then the soft behavior of the graviton and the dilaton is given by this expression, and you see that you get a string correction here for the sub-sub-leading term of order Q. You get also string correction in heterotic, but not in superstring. If you project... Yeah, I'll come to this. Yeah. If you project along the dilaton, that's what you get, and you get a term like that and a term like that. And if you take the generator of space-time scale and conformal transformation in momentum space, you see that those generators appear in the soft expression. Now, if you restrict, let's restrict us to the term of order Q0. Forget for the moment the term of order Q. That is the expression that was already present in the paper by De Mol et al. And this expression, this can be written in a more suggestive way, remembering that the amplitude for n particle in string theory has this the correctly normalized amplitude as this factor, and then a function which is dimensionless here. And kappa d in string theory in d dimension is given by this expression in terms of alpha prime and gs. Now, the fact that Fn is dimensionless, you can get trivially this equation. You can see that this equation is trivially satisfied. If you put together this equation with the soft theorem equation, you cancel this term, you get this term here, and this term can be rewritten in terms of derivative with respect to gs. So, and so that's the result that you get if you have only closed string as external particle. If you include open string as on a DP brane, now you get exactly the same expression, and that is obtained by the fact that in the case of, if you have open string as external particle, you get a term proportional to eta mu nu. You remember that that was in the, that term is needed in order to get the same expression. And so in all cases, the amplitude of the soft dilaton is obtained from the amplitude without the dilaton by a simultaneous rescaling of the Regge slope and the string coupling constant. And the same rescaling leaves the Newton constant invariant. So that equation tells you that there is no fundamental dimensional constant in string theory. Now let's apply this to the case of 5 dilaton. So this will be the soft theorem. So this is the amplitude with a soft dilaton, and that is the amplitude without the 4-point dilaton amplitude, which is this one. In the field theory limit, you can neglect the ratio of gamma function, and so that's the limit of supergravity. And so one gets 0 because one gets a homogeneous function of degree 2, you see here, and so this quantity gets 0, and so this is not in contradiction with the soft theorem, because in supergravity there is a Z2 symmetry, so only the amplitude with an even number of dilaton are different from 0. And so the soft theorem is consistent in the supergravity limit with this. Sorry? This is bosonic, but it's true also in the superstring. I think it's, yeah. And so in the field theory limit, you have to impose this, and you have to impose also the one on order Q1, and that has been the fact that these two equations, those people analyzed these two equations, and they established that there was a full conformal invariance in d dimension, provided that you introduce a scaling dimension which depends on the number of external leg. Now, let me discuss the origin of string correction. In the closed bosonic string, if you consider the amplitude without the polarization, the 3-point function contains also string correction. And the correction of alpha prime, they come from the Gauss-Bonnet term, and R cube, alpha prime square, from the R cube term. Now, suppose that in the pole term you keep also the string correction, then if you go to the procedure with the extra term, then you get also the string correction in the sub-subleading term. So, sorry, the sub-subleading string correction are completely determined by this term here. There are string correction in the heterotic, but not in superstring. However, you have string correction when you project on the dilaton, both in the heterotic and in the bosonic, there are never string correction. They cancel. Now let me go to loop diagram. That's a good question. That's an experimental result. It's a bit like the function f. Why the function f is only there for this particular case? I cannot give an answer.
From the point of view of the effective action, you cannot understand that? I mean, the analog of the R cube.
I mean, if you get the effective action, then when you look at the 3-point function, you have to include the term beyond Einstein gravity,
right.
and
there are no such terms with the dilaton?
it doesn't seem so. I mean, from the calculation.
The dilaton always comes as e to the minus 2 phi multiplying the whole thing.
Is what there?
The dilaton coupling is always e to the minus 2 phi, and then you have something independent of the 0 mod of the dilaton.
Yes.
So can that be used to explain this?
So this is an Einstein effect. This is a very different way.
Yeah, but the S matrix is independent. Right? So
So let's go to multi-loop. And now in the bosonic string, you can write in a very explicit way the multi-loop amplitude for any particle, any physical state. Here I wrote for one graviton, dilaton, and tachyon. And this is given by this expression where Z is the Koba-Nielsen variable of the particle which will become soft. And you get the H-loop Green's function. And then you get abelian differential and period metrics. Now, this, and then you have here the integral over the other Koba-Nielsen variable and the moduli. And this measure is quite explicit. In fact, if you compactify 26 minus d direction on circle, then that comes from the integration of momentum in the non-compact direction, and this piece comes from the sum of the momentum in the compact direction. And in the Schottky parametrization of the Riemann surface, the moduli are the multiplier and the fixed point of the Schottky generator. So you have the complex plane, and you put 2H circle, the isometric circle, and you identify them, and that gives a description of the Riemann surface with H loop. The Schottky generators are, this is a projective transformation which has 3 parameters, and one is the multiplier, and the other 2 are the 2 fixed points of this transformation. So this is very explicit. And maybe also to make connection with people have been discussing in string field theory, and also the discussion on ambitwistor, where people seem to be using a formalism which is pretty much the same what people have been using in string theory. Let me say a few more words. In fact, what you do, you start with a BRST invariant string vertex which has n plus 2h vertex. This is a BRST invariant version of the one that Lovelace introduced in 1970. Then you can take this vertex, and you can use and this vertex you can prove that is completely BRST invariant. Then this vertex contains the function vi of z, which specify the parametrization around each puncture. And this is an essential condition. However, in the old days, Lovelace introduced fix this function, imposing that these 2 other conditions. And these are the conditions that completely fixed. You can do the same for closed string. There's no. I mean, it's more difficult to understand why, because in the open string you have planarity, but you can do in this closed string you get there's no inconsistent. Now. And so by this solving process, so you need a BRST invariance vertex and a BRST invariance propagator, and then you close, and then you get a vertex which has now, which is this one, which is n external particle H loop, and you see that there is a vacuum of oscillator here. And there are both alpha and alpha bar, and instead of having the object that you have on the sphere, you get the object that you get in the Riemann surface. I should remind you that this calculation was done before that people understood that there was a string theory underlying the model. So this function here, which are well defined on the Riemann surfaces, come out automatically by the gluing procedure. So this is the whole vert. So when you specify now this expression for the states of, let's say, n-1 tachyon and 1 graviton and dilaton, then you get this quantity here. And now, if you compare that amplitude with what you get at the tree level, you see that the expression is the same apart from this extra term. This extra term is not appearing at the tree level. For the, yes, eta mu nu, which contributes only to the dilaton. Now, for doing the soft limit, you don't need to know the explicit form of the Green's function. You need to know only the general property. You need to know that the double derivative gives the delta function plus this term here, and this term here, this condition imposes this relation. And you need to know that the Green function at the same point goes to 0 here, because the prime form goes to 0. Now, these conditions are the only condition that you need to recover the soft theorem. And so you get exactly the same soft theorem at the tree level for the graviton. For the dilaton, you get an extra term. There is a delicate point that the integral of moduli is infrared divergent. However, if you regularize both the amplitude with n+1 particle and with n with an infrared cutoff, and we keep d not too low, then the soft operator stays the same. And that's what you get. So this is exactly like the tree diagram, and this is the extra term that you get for the dilaton. And so this is actually at the order Q. At the order Q, this term, you have to expand the Green's function here, so you get a term containing this quantity times the Green's function, okay? That a priori is not 0. So this will be a modification of the soft theorem compared what you get at the tree level. Now, if the contribution of the Q, if you use, and I will come to that later on, if instead of using the, well, I didn't write I mean, you have to use the Green's function, which is or Arakelov Green's function. If you use this Green function, then the difference between the Arakelov Green function and the other Green function disappears because there is on shell because of momentum conservation. However, if you use this Green function, then you can show that the extra term that you would get here get cancelled at multi-loop level. Okay, also in this case, yeah. But when you compute off shell, the explicit amplitude doesn't depend on which one you use. Yeah. For the dilaton, you get an extra term. At q to the 0 level, not at the leading. The term which is 1 over q is totally proportional to the mass square. And that is a behavior that is shared by the Nambu-Goldstone boson dilaton. So now you can write the H-loop and tachyon amplitude, and which is given by this expression. This is the correctly normalized one, and again, as the following form. Now you have compactified, so here you have also this ratio, and this is kappa d.
So you keep the momenta only in the non-compact direction. The ki are in the non-compact direction.
Yes. Then, because of the previous relation here, you can trivially check that this equation is satisfied, which here you can write in terms of GS over GS. And then you use this equation together with the soft behavior, and then you get, so this is the soft behavior. If you use this equation in the previous equation, you arrive to this equation, which is precisely as in the case of the tree level. And so this is the term of order q to the 0, and all the other terms as in the tree level. So essentially, this extra term here seems to be important to get a behavior which is the same at each loop level. Now, let me discuss briefly the infrared divergent in the bosonic string. There are no ultraviolet, but due to the tachyon and dilaton tadpole. Let me do an example. You take an amplitude, one loop, and tachyon, and this is the amplitude, and this is the measure of integration. If you go, you consider the regional modular space where all the nu are close to each other, and nu n is 0. You see, in the previous expression, you fix, you integrate over from 1 to n minus 1, and you fix a nu n at 0. So the limit in which all the nu goes to the same point, you can be reached by introducing epsilon and phi in this way, and epsilon is taken to be 0. For small epsilon, you can neglect all the quantity which is in this product here, and that's what you get. And then you regularize the infrared divergent, giving a small momentum to the term here. And then you expand this, and you get essentially, this is an amplitude in which you have a tachyon going to the vacuum, and which has been regularized by this term. And here you get a dilaton going to the vacuum, which when you take q to 0, you go to 0. So this is the amplitude. You have to regularize also the integral over tau, because of in this limit. But you see that the previous do not depend on the number of external legs, and therefore you can regularize both sides in the same way, and the operator connecting them is still the same. However, if you go to small d, in this limit, you get infrared divergence which depend on the number of external legs that was already known in '82 by this paper by John. And those infrared divergent will change drastically the soft operator. Now, there are other problems because if you have a massive string, they are plagued also, the divergent, they require mass renormalization. They can be regularized, keeping the Coba-Nielsen variables not close to each other. Again, they depend only on the number of external massive particles, so do not seem to change the soft behavior. Now, let me say a few words about the Arakelov-Green's function. From the formalism that I was explaining before, the Green function coming out from the calculation is not only this space, but contains the object which parameterize you parameterize around the puncture, the coordinate around the puncture, and this Vi Z satisfy this condition. Now, if the external states are on shell physical state, this term drops out. Now, in the old review by Docker and Fong, the regularized Green's function in the conformal gauge is given by this expression, where this rho is the metric of the Riemann surface in the conformal gauge. Now, if you, and this Green's function is invariant under the transport along the cycle of the Riemann surface. And you can check also that under a conformal transformation, the two objects transform in the same way, and therefore you can identify them. And that's the first step to make the two expressions here to be the same. In addition, you have to introduce the Arakelov metric, which is given by this relation. This object here, containing the metric, is identified with this one. And once I identify the Arakelov metric in this way, then you can define Arakelov-Green's function, which satisfies this equation. Now, the previous equation do not completely determine G, because there is a double derivative, so if you have one G, you can always add plus holomorphic plus anti-holomorphic function, and you can use this freedom to fix also this equation. And so this is the equation that the Arakelov metric satisfies, and this is the equation that eliminates the order Q extra term that appears in the case of the dilaton. So another way of identifying rho with the VI, if you take the end region vertex, which is an expression, remember that the end region vertex was an expression which was valid off-shell, and off-shell contained this parameter because that was used to compute multi-loop. So you have to be a bit off-shell. On the other hand, you can do the functional integral Apolyakov, and in defining the Green's function, you have also the term where I equal J that you have to regularize. This term can be regularized in a conformal invariant way, so they include this G, and that's the expression that you get. And so you see that these two expressions are the same if you take this identification. Now, I am not going to go to the field theory dilaton. Let me just now let me just give an example. Suppose that you consider a conformal invariant version of the X potential. So you have two fields. Instead of in the X potential, you have a constant here, so you don't need that extra field. Here you have two fields, and you have, and so the Lagrangian is classically conformal invariant, And so there are flight direction corresponding to, you can choose the vacuum expectation value to be A. A can be anything. If you take A different from 0, the conformal invariance is broken, and in terms of those fields, you get this Lagrangian here, where the air field has a vacuum expectation value, and this is the massless dilaton. Instead, the other field gets a mass. The question is, you can compute amplitudes in this model, 3 amplitudes, and you can look what is the soft behavior. If you do explicit calculation, you find that the amplitude with n massive state and 1 massless, you get this behavior here. And this behavior can be shown to follow from the word identity of the dilatation current and the additional point that the trace of energy momentum tensor is proportional to the second derivative of the dilaton field. So that's the soft behavior that you get from the field theory dilaton, and this is the soft behavior that you get from the string dilaton. So the difference is 2 and 4 minus n here. Now, in the Nambu-Goldstone boson, all dimensional factors are rescaled by a scale transformation, and you get this factor here. But in string, you rescale only the factor 1 alpha prime, but you keep kappa d invariant fixed, and that's the difference of the two behavior. Now, all this can be computed by looking at the word identity of dilatation and special conformal transformation. And so in field theory, you get this behavior for the dilaton, and there it's natural to have generators of dilatation and special conformal transformation. And these terms are present in the case of the field theory dilaton, but are not present in the case of the string dilaton. Okay, let me come to the conclusion. So if you impose those conditions which are required by gauge invariant, and giving the structure of a 3-point function, you can fix the 3 leading terms of the soft behavior of both the graviton and dilaton and the leading term of B mu nu. In general, f can be an arbitrary function, and if f is arbitrary, this will prevent to get a soft behavior for the dilaton. But looking at string theory, you can see that f has a very simple form, and is most of the time it's 0, but is non-zero in a specific case, and in this specific case, as a physical, you can find a physical explanation. Now, the result for the dilaton seems to be completely free from string correction. So it seems to be the same superstring, bosonic, and heterotic. The string correction appear only in the graviton, and that can be explained in terms of the string correction that you have in the 3-point function. Now, the soft behavioral dilaton contains a generator of special conformal transformation, and they appear also when, for the field theory dilaton, the two soft limits are similar but not equal. And this comparison is true at the 3 level. Of course, at loop level, the conformal invariance is broken, so there is no, so the dilaton in general acquire a mass, while accepted in certain theory, like n equal 4 Young-Mills, where the dilaton can be studied to any order of perturbation theory. On the other hand, the graviton stay massless in string perturbation theory and has the same behavior at the 3 as at loop level. Now, why the soft behavior of the string dilaton contains a generator, and why the function is so simple? This is left for the future. Okay, thank you very much.
time for a few questions. I mean, coming back to this Dilaton topic, I mean, if you take the effective action of string theory at 3 level, you diagonalize the static part, and you define what is the canonical field of the Dilaton, then you should be able to see from the effective action what are the
You mean the effective action in string theory?
The string theory expanded to some powers of derivatives. So as Oshlasher was mentioning, of course, in the string frame, you only have e to the -5. Okay, you have to diagonalize everything and to define exactly what the canonical field is. And then, since I think the effective action is known to some order, I think there are terms which, I don't know, contain r times d phi squared. We should be able to...
Yeah, we have not looked at this.
And the other thing is, when you go to loops, I mean, you have this G string, this G string you have at some point. So I would have imagined that the soft theorems of the Dilaton are strongly dependent on the order in the loop. Precisely because the Dilaton appears with different strings, the phi, say, not the physical Dilaton.
Yeah. So you would expect a different behavior.
No, I mean, it seems roughly consistent with what you say. I mean, you have GS, DDGS, which should be related to the genus.
But this becomes, I mean, in the formulation that Kongao was giving, this GSG becomes tau d tau, if I understood well. Tau 2, tau is the C0, the axion.
That's right.
Yeah.
Yeah, that's right. So, I mean, is that guy. Now, how is that guy related to your Dilaton? I mean, there should be a connection.
Yes, yes.